So last time we did random graphs. Today we'll do something called randomized rounding. So in particular, we'll do an algorithm today. Last time I sort of broke the rule because I didn't really give an algorithm. We studied some random process, but hopefully it was still fun. Whatever. We've been doing a lot. This is just, I guess, a quick recap. So what are we doing today? Today, we are going to look at three problems. We're going to look at max stat again, which we did earlier. We're also going to look at a problem called set cover, which you might have seen before. And then we probably won't have time for covering integer programs. That's okay. And so today, it's going to be about doing approximation algorithms, but trying to take advantage of something called linear programming. So it's about that as well. So, okay, so this randomized rounding is at some level, two themes at play. One is we're going to see how to bridge polynomial time and NP-hard problems with approximations, right? Because we don't have algorithms for NP-hard problems. And we're also going to bridge two different worlds between continuous optimization and discrete optimization. And we'll see how randomization sort of takes us from one into the other. So, okay, so what's an integer program? So these are these mathematical kind of simple programs where the variables are forced to be integers. So you might have an objective like minimizing or maximizing the sum of xj's, where the xj's are your variables. And then you have these linear constraints like a1x less than equal to b1. There's some kind of row of coefficients and it has to be at most some quantity. So there's all these budget constraints. There might be equality constraints. And you can also have these covering constraints. So the sum of x's, some kind of sum of x's has to be at least this or at least that. Okay. So, the C's and B's and A's here, those are all like fixed parts of the input. The variables are the x's. Okay. And the key thing is that the x is required to be an integer. Okay. So this is easily NP-hard because you can use it to model just about every combinatorial problem you can think of, and we'll see some examples. Okay. But it's also a very useful model, right? It's a very broad, versatile thing, and many things that you want would be written down naturally as integer programs. So, do A and B have to be integer? No. A and B do not have to be integer. So if you loosen this requirement that your variables are integers, then you get what's called a linear program. So the only difference is we replace this integer requirement, and now x is allowed to be real valued. Okay? But otherwise, your constraints and everything is still basically a linear equation. You're just summing things up with some coefficients. Okay. So the key thing, or the key difference between linear programs, integer programs, is that we actually have algorithms for linear programs. Okay. So, okay, so you imagine they might be useful, right? Because it's very natural to describe things as linear inequalities. So the first kind of LP algorithm we had is this famous simplex algorithm, due to Danzig, and supposedly do you guys know the story of Danzig discovering the simplex algorithm? So he was a graduate student, and the teacher, he was running late to class, and the teacher wrote on the board like, oh, here's a big open problem, trying to find an algorithm to solve linear programs. But he was running late to class, and he thought it was a homework problem. And he went home and came up with a simplex algorithm. It wasn't completely out of nowhere, because during World War II, he was doing operations research, and they're doing some kind of similar algorithms for very special cases. So there is some. But anyway, so he just kind of showed up and turned it in. The teacher's like, what the hell is this? Okay. So this actually turns out to be a really practical algorithm, but it's actually not polynomial time. And there's a big open question for like a really long time. You know, you can find in Edmonds Blossom matching paper, for example, to come up with a polynomial time algorithm for the simplex. I mean, for LP. It wasn't hard to come up with an example where a simplex has a tough time. And so the first algorithm shows up in 1979 from Kachian using something called the ellipsoid algorithm. Okay, it was a bit of a theoretical, I mean, wasn't super practical, and it's using something called the John's ellipsoid theorem. So it's really a matter of high dimensional geometry. And then Carmarker did something called the interior point algorithm. This is much more like convex optimization, where you have a big potential function with certain exponential things, and if you work it out, you will get a weakly polynomial running time. So that's also an important thing. So it's polynomial in the number of bits, which is often just fine for practice, but getting a strongly polynomial time where you don't get any credit for long bit numbers, it's just like kind of arbitrary real values. Trying to do that in strongly polynomial time is like one of the biggest questions out there. Either to do it or to show you can't. Okay. So at some level, I think of integer programs as a representative for discrete optimization. Linear programs are representative for continuous optimization. The only difference is one, the variables are continuous. The other one, the variables are unique. But there's a world of difference because integer programs are NP hard and linear programs have algorithms. Okay. Today, at some level, since linear programs obviously look very similar to integer programs, the high level question is, can we use linear programs to help us out? We won't solve integer programs exactly because it's NP hard, but maybe it can help us approximate integer programs. Okay? So this is called, yeah, LP-based approximations. Okay, so the setup is you're given some kind of combinatorial problem. Okay, you don't know how to solve it. You want to get the best possible answer, of course. And step one is going to be to try to model this as some kind of integer program. So you write down some integer program. Usually this is not too hard, and we'll have a couple examples today. Step two, given an integer program, okay, you can't do much with it. So what we'll do is we'll look at the corresponding linear program. So all I'm doing is removing the integer requirement, okay? And I'm left with a linear program which resembles my original problem. And we'll give that to some black box LP solver. Okay, so this is, some open source code or something. But all we care about today is that LPs can be solved in polynomial time. So I'll feed it to the LP solver, and that'll give me some kind of solution, right? It'll give me an optimal solution for the linear program. Okay? And in general, it's a good solution except for the fact that it's not integer. So if I was going to like maximize or something, then the objective value I get here is going to be at least the objective value from the integer program, because all I'm doing is allowing for more possible solutions by allowing things to be continuous. So the value is going to be good, and it's going to satisfy the inequalities, but the issue is that I really want integers. I want something that corresponds to like yes-no decisions or something, right? So that's like a whole family of different approximation algorithms, which are like, okay, I know the LP is good. It also gives me a good reference point, right? So if I can take x and convert it into an integer z, and let's say I'm maximizing, and let's say z has at least half the value as x, and x definitely has value at least opt, because the LP is a relaxation of the integer program, then z gets you at least half of opt, right? So not only is it like a reasonable heuristic, but you can also often compare the values and really say, okay, it's NP hard, I don't get the perfect solution. I always get at least half of opt, right? So this is how we approach NP hard problems. And so today, I mean, you can teach a whole class on different approaches, right? But anyway, so this step is sometimes called rounding, where you go from the continuous values to integral values. So okay, so that's sort of the life cycle we'll be looking at, and we'll do a few problems to see why this is useful. Okay. So we'll start with a familiar one. So we did max at the first lecture. So I give you some formula. You want to satisfy as many clauses as possible in the approximation version, right? And we did this silly algorithm where we just looked at, trying a uniformly random assignment and showed that for 3 sat, it'll get you 7/8. In fact, for 4 sat, 5 sat, it will do even better. And besides, that was just linear expectation, but besides doing a random algorithm, we even de-randomized it, right? So that was cool. Okay, so that was for 3 sat. The only difference today is that I'm going to allow any number of variables in the clauses. Okay, so it's a SAT formula, but some may have 5 variables, some may have 10, some may have square root n, I don't know. Okay, so, and the goal, like before, is to satisfy as many of the clauses as possible. So, now, okay, so there's a slight difference that I want to explore between ksat and maxsat in terms of the bounds we get. Okay, so think about our oblivious algorithm, okay, and which was just a uniformly random assignment, which will get different approximation ratios for different values of k for ksat. 1 sat means 1 variable per, 2 sat means 2 variables per. So, okay, so we're going to fill out this table, starting with maybe an uninteresting row. So for k equals 1 sat, for some reason the clauses are each giving you 1 variable each. If I did the oblivious algorithm, I just did a random assignment, what approximation would I get? Half. Okay. And what if k is 2? So now you have 2 variables per assignment. What approximation would you get? 3/4. 3 sat we did last time, that's 7/8. What if it's 4? Okay. And so this will always be 1 minus 1/2 to the k or something, right? So this gets much better for larger values of k. What about max sat? What can we guarantee? 1/2. Okay, so this is absurd. Our algorithm only gets 1/2 for max sat, which is what you're getting for 1 variable, which is something you shouldn't be using a randomized algorithm for, right? With 1 variable, you should just look at it and solve it, right? So this is sort of absurd. This is what we want to rectify. Okay, so we're going to try to do better. This time we're going to give an algorithm that actually looks at the formula for a change. Okay, so we are going to try to do something like this. We'll try to figure out how to model this as a mathematical program, and then we'll figure out how to turn it into an assignment. Okay, so I set up some space so we can fill it in together. So we're going to try to write an integer program for maxsat. Okay, so we need to fill in the objective, the max part. Subject to would be some constraints. And I've already set up the variables for you. We have 1 variable for every clause, so zi for the ith clause. And we're going to try to model it where 1 is supposed to mean the clause is satisfied, and 0 means it's not. And I have yj's, which is 1 if I'm setting the xj to be true, and 0 so that xj is equal to false. Okay, so my goal is to write down sat and re-express it in this language. We can start with the objective. Okay, so the sum of zi, this is, okay. I want to satisfy as many clauses as possible, right? Okay. Now, obviously, we have to put some constraints on it, because otherwise you just set zi to be 1. So you want to show that you can come up with some assignment corresponding to your zi's, modeled by these variables yj, right? So somehow we should come up with some equation so that, I can only set z1 to be true if the assignment is true or something. Yeah. Okay, so you said zi is greater than or equal to the sum over first, let's look at the variables j, where xj appears in, I guess, clause I, like not negated. And then what did you want? Oh, well, what should I write in the sum? Yj plus, and then I guess summing over all the literals that appear in the negated form. Uh-huh. 1 minus yj. Okay, so that would, for example, it would be something like z1 is greater than or equal to y1 plus 1 minus y2 plus y3. Okay, are we happy with this? Yeah, less than or equal to. Less than or equal to. So you have to set one of the variables, I mean, you have to get 1 point from either here or here, and then you're allowed to make zi that big. And I guess, yeah, I've already forced z to be 0 or 1. So there's always this upper bound of 1. You're not allowed to get 2 points. Okay, so that's a simple integer program. Here it is, whatever, it's a little better handwriting. For every clause ci, that part on the right, of course, is important, right? There's many of these constraints. Okay, so the linear program is the exact same, except now y is between 0 and 1 continuously. Same with z. Okay, so somehow this thing we can actually get the solution for. Okay, and as mentioned before, since the linear program only allows for more possible solutions because you can have fractional values, the objective only goes up. So when I get the solution, the y's and the z's, I know the objective is very good, and the only issue is the inequality. Okay. So now here then is our, sort of like our big question, right? Is that at some level the LP is giving me some kind of hint. Here's something like an assignment. It's giving me values between 0 and 1. And so I want to take these fractional values and ultimately convert it to an assignment, true or false, right? That's what we want to output. And at some level, the basic question is like, okay, so like 1 probably means you should set it to true. 0 probably means you should set it to false. But like, what the hell does y1 equal to 1/2 mean? Set what? Oh, so maybe round up, just deterministically, if it's at least 1/2, round up? Yeah. Sure, you can repeat the algorithm with things, but it'll just give you the same answer again, right? Oh, well, you can assume it's not going to give you anything that's 0 or 1. Yeah, I feel like it when I was in English class in high school, there was some like silly philosophical question of like, what is half a chair? Like if it only has 2 legs or something, it seems to be a chair. But in randomization, we actually have a very good answer for what does it mean for y1 to be half. It means half the time it's 1 and half the time it's 0. So the randomized answer to what is half a chair is a chair that's there half the time. So let's look at this. I don't know if that's too small. Let me zoom in. So for each of these variables xj, I'm going to take that probability yj, that yj value and interpret it as a probability of setting it to be true. So first, it agrees with our intuition. If yj is 1, you always set it to be true. If yj is 0, you always set it to be false. But if it's like 1/2, it's like half and half. The LP doesn't have a strong opinion, neither do we. If it's 3/4, it'll be true more often than not. Okay, so that's what we're going to look at as an algorithm. So, okay. So now we just need to analyze this thing. So here is the claim. For each of these clauses, we're going to satisfy the clause with some constant times zi. So the LP might have said like, oh, you satisfied this clause 0.66 or something, right? We won't quite get 0.66 points necessarily from this strategy, but we might get 1 minus 1 over e times 0.66. And that's what we want to show. Does the claim make sense? No, z is what was given to us from the LP. So the LP gave us y and z. It's the Euler's e. Yeah, well, it'll come up. Actually, it'll come up a lot in this class. Yeah, you're going to be good friends with. Okay. Um, so the sum of z's we know is good, right? The sum of z's is at least opt. So if I can show that each clause I'm getting like half of z, then at the end we'll get half of opt. In fact, 1 minus 1 over e should be a little bit more than half. It's like 0.68 or something. Um, so we're going to show we can get 0.68 of opt on average, maybe. Okay. So right now we're just analyzing one clause, and I want to get something proportional to zi. Okay. So how do we analyze this? We can make this a little bit more concrete. Let's say that I'm looking at C1, which is equal to like X1 or not X2 or X3. I'm sure if we can figure this out, yeah. The expectation of the summation that we use to bound Zi. So, okay, let me write down the constraints. For this, we would have Y1 plus 1 minus Y2 plus Y3 is greater than equal to Z1. If I took expectations of this, what do I get on both sides? Exact same. There's no randomness here. Okay. But it probably is helpful for me to write out this equation, right? So the algorithm, x1 is going to flip heads with probability y1, and x2 is going to flip heads with probability y2, and x3, right? So what is the probability that, yeah, all three have to fail. So that's going to be like 1 minus y1 is the first one failing, times y2 times 1 minus y3. Okay. Now, how do I deal with this? This is a messy polynomial, right? You wouldn't want to watch me factor it. And you can imagine we'll have bigger clauses than just three. The more general one will look like this. All right, suppose I just want to deal with these two terms. How might I do that? So when we analyze things, multiplying things together is a pain, right? But adding things together, life is better. I want to turn multiplication into addition. Uh, but not use log, because log is also a pain. Or maybe implicitly similar. Yeah. Oh, no. Fake hand, okay. We actually have done this in previous lectures. So 1 minus y1 is less than equal to e to the minus y1. 1 minus y3 is less than equal to e to the minus y3, right? And now in those exponents, these things are adding up, right? How do I deal with y2? Sorry? Well, we can write y2 is equal to 1 minus 1 minus y2. 1 minus y2. Okay? And then, now we get e to the negative y1 plus 1 minus y2 plus y3. Okay? And what is this quantity? Uh, I guess it's going to be less than equal. The exponent is greater than equal to. So this is at most z1. Okay? Just like how this one will be at most e to the minus zi. Okay? So now I still have to do something like this. Which I only vaguely remember, so hopefully I get it right. Okay, so let's look at this function. F of x is equal to e to the minus x. We're actually going to do something different. If I remember correctly. So this is a function that looks like this. Okay, where this value is 1. So this is actually a convex function. Okay, so somewhere here is 1, and somewhere here is zi. Okay? And if we use convexity, so this value here is like what, zi times 1 plus 1 minus zi times e to the minus 1. So this point on the straight line, right? So if this is 1 on the x-axis, this will be e to the minus 1 on the y-axis. Maybe I should write that differently, sorry. So if I looked at the y-axis, not the best handwriting ever, but you're used to that. It should be like e to the minus 1 there, right? So this is a straight line in between. So what is this? Is this like zi times 1 plus 1 minus zi times e to the minus 1, or did I get it backwards? I'm crowdsourcing here. Well, we'll just see because we know what the right answer is. Okay, so this is zi at most zi times 1 plus 1 minus zi times e to the minus 1. Okay, so it should be the opposite. So you just baited me into this. Okay. 1 minus zi times 1 plus zi times e to the minus 1. Does that get what we want? Hopefully. Okay. Uh, I'm not gonna undo. I can't undo anymore. The undo stack has been ruined. Okay. Do we do it correctly or do we get it backwards? Okay. So this is okay. Okay. In a paper we just write the equals and we skip the calculation. Okay. Okay. But you get the idea. You get the right convexity correct and you do it slowly. And you'll get 1 minus 1 over e zi. Okay. Somehow this is a little bit better than Taylor expansion. Okay. If you do one clause, then you're going to be able to show an expectation you're getting this much. Why? Yeah. So what's the buzzword? Linear expectation, right? I'll write this as a summation of clauses. The first clause gets me 1 minus 1 over e times z1. The second clause gets me 1 minus 1 over e times z2. Now, so then you get 1 minus 1 over e times the sum of z's. And then the last important point is that the sum of z's is at least opt, because that's coming from the LP, right? So that's not hard arithmetic-wise, but conceptually really important that we're able to relate to the optimum value. It's better, in fact, it's related to the LP opt, which might be slightly higher than the integer opt. And so that's our approximation algorithm. Okay. All right, so the question is, can we do better? Okay. So, okay. 1 minus 1 over e, that's better than 1 half, which is what we had before. But what would the algorithm get if you only had one variable? That exact same algorithm. So if a clause had only one variable, so it's just like yi and or yj and zj, right? And then we don't have to multiply anything together. With probability yj, you get a point, and zj will be the same as yj, right? So if ci has one variable, then sort of like probability of success is going to be equal to zi and stuff like that, right? So okay, huh? So okay, so let's say that ci is equal to xj. So the probability that we satisfy ci is going to be equal to yj, and that's at least zj or zi. So the one variable is easier. We don't have to do all this calculations. And if you had two clauses, so let's say that c1 is equal to x1 or x2, maybe we can also do a little bit better. So you'll get, oh, did I do a one? Oh, did I screw something up? Oh, okay. I think I know part of our source of confusion. So that's the probability we fail the clause, right? So somewhere around here, okay, so we would need to do a 1 minus. So in other words, what I want to show then ultimately is that 1 minus e to the negative zi is at least 1 minus 1 over e zi, which I think if we had done whatever one way or another, we would get correct. Okay, let's just keep going. All right. Um, but if we look at this, so if I look at 1 minus 1 minus y1, 1 minus y2, okay, then you'll get something like y1 plus y2 minus y1, y2. No, maybe, yeah, is that correct? Okay. And how does y1 and y2 relate to y1 and y2? I want to get rid of this product. Should have brought my notes. Yeah, that is true. Uh, that is true. Um, so what's AMGM? You know the AMGM inequality? Something like this? Sorry, I think my brain is fried from teaching 2 classes. Um, is that going to be useful for us? Okay, so this is at least y1 plus y2 minus y1 plus y2 over 2 squared. And y1 plus y2, I guess is at most 1? No, that's not true. What's the conclusion? Sorry? Okay, I'm trying to get 3/4. Uh, how did I get 3/4? Okay, we want to get 3/4 of zi. I don't. 1 minus y1 minus y2 plus y1 y2. Oh, okay. Oh, 1 minus y1 plus 1 minus y2. And then we'll get 1 minus y1 plus y2 over 2 squared. Sorry? Z1 squared. Oh, and then Z1 is at most 1. Is that okay? Feels like we cheated. Can't I just do what? Doesn't someone have my notes on their laptop? Yeah, I used to know this really well. I'm just blanking. Well, you teach me. What should I do? It's a little embarrassing. I've never blanked on this before. I've done this many times. Um, okay. Okay, so we are doing something like over here. That's P not satisfied. This is not. So, okay, I'll apply AMGM to this. So I'm adding them up, dividing by 2. So that's like 1 minus, I don't know if this is the right way to look at it, over 2 squared. You believe it? Okay. Squared. Because y1 plus y2 is at least z1. Oh, so now I'm doing convexity for the 1 minus x squared. For this convex function. Oh, over 2 squared. Somehow zi over 4. Oh, it should be. No, it could be a fractional value. This is the LP solution. Sorry, you want to read off the last line? How do I expand this out? Or deal with the convexity? Just say it out loud and I'll write it and then we'll pretend I did it correctly. What the hell is quantity squared? What? Oh, okay, sorry. So this is just zj of the time we evaluate at 1 and 1 minus zj of time. This is the interpolating the line and just doing it correctly. So you get 1 minus zj plus zj over 4. So you get 1 minus 3/4 zj. Okay. Well, we'll only do one application today. That's fine. Uh, So 1 minus 3/4 zj if you do it all correctly. Um, okay. Okay, well, it's good to know, good to know that anyone could do this. That's the learning lesson. Okay. Um, so what's the point? The point is that our algorithm. So on the left we have these oblivious things that are very good for large k, but very bad for the first 2k. And our LP algorithm is actually doing better for the first 2k's than we realized. Okay, the k equals 2 is a bit messy. Um, uh, okay, and I'm trying to get better than 1 minus 1 over e. Now, what is the average of the top two rows? Top row, sorry, the top two columns in the first row. Or, okay, what I'm saying is somehow the average of these two scores is always at least 3/4 zi. Okay, and same actually with all the other ones. The second row also I mean, one is bigger than zi. So, in fact, all the way through, you're always getting at least 3/4 zi, where the bad case is k equals 1. Okay. So here's the fun part. Can we get at least 3/4 altogether? So at some level, what I'm saying is that on each particular tier, I'm getting at least 3/4 zi. But any single algorithm can be flawed, right? This one's going to do great on large k, and this one's going to do great it's going to do better for really small k. The LP is actually going to look at the formula and do something smarter. So the question is, how can I try to get 3/4 overall? How can I sort of get the best of both worlds? I have two algorithms that in some weird sense on average will get me a 3/4 approximation. Sorry? And how would I argue that actually gets better? I have two algorithms, don't know which one to choose, don't know how to mix them. Yeah? Oh, so you can't do anything on a per clause basis. Like you can't oh, this clause is small, I'm going to follow the LP. This clause is big, I'll obliviously round. Because what if they share variables? X1 is in both, right? Yeah, that's right. So I'll flip a coin. If it's heads, we'll do the oblivious rounding. And if it's tails, I'll round the LP. This feels like we're running both algorithms and getting half the benefit of each without actually running both algorithms and getting half the benefit of each, right? So I was trying to figure out how to get the average on a per clause basis, but different clauses, do better for different strategies. I know the average strategy is good. So if I flip a coin and I now look at a particular clause, with probability 1/2, I do probably the worst strategy. Probably 1/2, I do the better strategy. And the average will get me 3/4 according to the previous table. Okay. So in this way, we can actually blend our two algorithms and we get a 3/4 approximation overall. Yeah. Yeah. Now that you know that one or the, on average, they're the two, now you can say, oh, now I can run both and take the better one. Yeah. Okay. Any questions? Yeah. Whose? No, I don't think this is Yao's lemma. But Andy Yao did a lot of stuff, so but I don't think this was his result. Yeah. Okay, that's it for today. And sorry for the goof, but it's more fun that way anyway. And uh, and so next time we'll do this set covering randomized rounding and maybe some online algorithms as well, which is pretty fun. So that's what we'll do Friday. Okay, so last time we did this randomized rounding, and that was really about approximating NP hard problems, and also about this distinction between continuous optimization and discrete. In short, like continuous programs, like LPs, are actually easy to compute. But integer programs, those are those yes, no questions, Hamiltonian path type questions. That's when things get hard. And so we're looking at algorithms of this general flavor where we're really trying to leverage this LP solver as a black box. So I can take whatever discrete problem I'm interested in, write the LP, solve it, and then figure out how to make use of that. So, okay, so what we did last time was maxsat, or at least we tried to do it last time. And the algorithm was, or the two steps was, we had to think of some kind of integer program to model trying to satisfy clauses. We did that. And then we looked at this algorithm that would try to just flip coins based with probability based on the LP to decide if a variable should be true or false. And then you do some analysis, and in principle you do the analysis correctly, and you show that every clause is satisfied with 1 minus 1 over e times the value assigned by the LP. We apply linearity of expectation, and then we'll get 1 minus 1 over e opt. And then there was this fun follow-up where we observed that our LP actually does better for the small values of k equals 1 and 2 if you just kind of directly analyze. And meanwhile, for large k, the oblivious approach does better. And in fact, for any particular k on average, you're getting at least 3/4. And the question is, how do you get, how do you actually get a 3/4 approximation? And the trick algorithm is, oh, you just randomly choose one of the two algorithms, right? And then you can work through the expectation. What's really telling you is that, oh, linear expectation is super useful, right? It's only from this expected point of view that you can get away with this. Yeah. It's the literal average. I mean, if I add this and divide by 2, I get at least 3/4 CI. Yeah. And the last question was, oh, is there some way then to combine it? Yeah. So somehow this randomized perspective, you can combine, right? You can kind of do half an algorithm and half an algorithm in a funny way. So we'll try another application, another standard problem. So this is called the minimum set cover problem. So I give you sets and points in space. So you might have seen this in your algorithms class before. So here I have n sets and they're covering some points. And my goal is to cover all the points with the minimum number of sets. Something like this. Okay. And is there anything else? So this is NP hard. Do you guys remember the reduction? Does anyone remember any reductions from their class? I taught some of you. Okay. Well, I guess I don't have any slides about the reduction. Sometimes I did. So let's try following our formula. Okay, so I left some spots blank. And, right, so I want to model the set cover problem as an integer program. Okay, and to keep us on the same page, I'm going to introduce a binary variable xj telling us whether or not we take a set. So xj corresponds to set j out of n. Okay, so we could start with, say, the objective. Okay. Sounds good. And now what are my constraints? So for a particular point, which is indexed by I out of M. Yeah. So we're using xj's to model the sets, like deciding whether or not to take the set in my solution. So what would my constraints look like? Yeah. How do I do? Okay, I guess I just do I in sj, xj. This should be at least one. So this is saying I'm taking at least one set for every point and trying to minimize the total number of sets. Okay, simple enough. Same thing. In a linear program, it's just going to go from 0 or 1 to between 0 and 1. This slight change makes the polynomial time solvable. So I can get a solution on the right, and I want to convert it to a solution on the left. Okay, just like last time. All right. So how am I going to take my sort of fractional set cover and convert it to a real one? Again, the question at some level is like, how do I interpret half of a set? So any ideas for rounding this? Yeah. Yeah, let's look at a random set where a random set cover where the probability of a set appearing is given by the LP. Okay. Oh, okay. I was supposed to do that calculation together, but that's okay. So we're looking at this algorithm where for every set, I'm taking it with some probability, right? And I'm letting F denote like the family of sets that come out of it. So F is some random set, random collection of sets. Okay. So the first step we should have done interactively by goofed up is, okay, let's look at the objective, the expected value of the size of F. That's the number of sets I take. And by linear expectation, I take some set 10 with probability x sub 10, right? And um, so we'll get opt. We'll get LP opt, right? Okay, good. Now, let's start analyzing things. So first, yeah. Well, because I solved the LP, so it's really less than equal to opt, because my goal is to minimize. So I get an optimal solution to the LP, and the LP is just a relaxation of the integer program. So anything that's feasible for the integer program is feasible for the LP. So the LP will get a solution that's at least as good as our original discrete problem. So the sum of xj's, which is the LP opt, is at most the true opt. Okay. Okay. Now, I thought as a starting point, we can fix a point I and ask, what's the expected number of sets covering that point? Okay. And so what would it be? A particular point. How would I go through this? Okay. So maybe I'll sum over the sets that contain I, the probability that I put SJ is in F. Right, it's the probability I take it, which is xj, which is at least one. Okay, so again, linear expectation. All right, maybe this was very easy. Okay, but we're really interested in what is the probability that it covers a point I, right? Because I need to cover all the points. That's really the only requirement. And I guess I gave you a head start by already negating it for you. So let's try to figure out the probability that I don't cover I. It should be less than equal to something because I really want to show the probability that cover I is greater than equal to something. Okay, so what should I write? Okay, the product of 1 minus xj over which j's? Okay, so this will be the exact probability, right? Because they all have to fail. Okay, now I have one of these messy terms. Okay, e to the negative sum of j, or I is in sj, xj, and this is at most 1 over e. So the sum is at least 1, but there's a negative sign. The sum is at least 1, but there's a negative sign, so you get the less than equal. Okay. Okay. So the probability that we cover I is at least e to the minus 1. Okay. 1 minus 1 over e. I'm just keeping you on your toes. Okay. All right. So good. Good. Now, here's the thing. The fact that I cover every point with constant probability does not actually tell us, for example, that it's a set cover with constant probability. Right? It may basically never be a set cover or close to never. Okay. So now our goal is to repair this. Okay. So in other words, our algorithm isn't strong enough. Just flipping a coin doesn't actually give us a set cover. Good, good. So I guess the question is, how can we make our algorithm better and actually produce a set cover? Yeah, okay. So there are in fact two approaches, and that maybe that's actually more natural based on what we've already done. So I want to make sure every point gets covered. Right now I have something where I pay opt, and then every point gets covered with constant probability. If I ran this like log n times, then at each particular point will get covered by one of those solutions with like 1 over n squared probability. Okay? And once it's 1 over n squared, I can take the union bound and say, oh, they're all covered by the total combination of all my random set covers. So that'll be a log n factor bigger. So that's rounding log n times. So each time you pay opt, you pay log n opt total, and then you can take the union bound. Okay, that's one approach. The slides are prepared for a second approach. What would be a second approach to strengthen our... Yeah. Yeah, let's try increasing the probabilities so that we can get each of those xj's back down to roughly 1 over n squared or something, right? Or each of those i's. Okay, so let's do this. Suppose I scale everything up by some alpha, and we'll figure out a good value of alpha afterwards. Okay, so I'm going to take the set Sj with probability alpha xj, or if it's more than one, that's just deterministic. We take it. Okay. All right, so Let's redo some calculations. What would be the expected cost of our solution now? Or size? So I scale everything up by alpha. Oh, you don't know. Okay. Who knows? Okay, why? So the probability that I take the set, uh, it just scaled up by a factor of alpha. All right. So we just scaled everything up by alpha. The objective goes up by alpha. Okay. So now let's go back to this calculation that we did before. How would I show what is the probability that F doesn't cover I? Sorry? Okay, so let's do it slowly. So we can do the same thing as before. All right, less than equal to 1 minus alpha xj. Well, so first, if there's a single set j containing the point I where the value is at least 1 over alpha, then we'll deterministically take a set, so that's okay. So now I'm just going to focus on the case where alpha xj is always less than 1, so that this thing is not negative. Okay. All right, so we do the same thing as before. Okay, and this time we'll get e to the minus alpha. Okay, so one thing kind of nice is that I'm getting exponentially decreasing, right? So if I increase opt and I pay a factor of 100, I'm getting e to the negative 100 on the other side. So that's kind of a nice favorable thing, right? I'm paying some linear overhead in the cost, but my satisfaction, everything's going down exponentially fast. Okay. So what would be a good value of alpha yeah. Yeah, not log n squared though. So if I did log n squared, well, that would be very strong. I would get n to the minus log n, 2 log n. Oh, okay. I got it. Uh, something like 1 over n squared. Okay. And then, and now if I want to look at the probability that's not a set cover, we're going to just sum over all the points. This is the probability of not covering that point. So here we're applying the union bound. And if we did alpha to be 2 log n, you get, oh, it's m, there's m points, but this is slightly besides the point. As usual, why do we choose the only 2 letters that are the same? Okay, and you get like 1 over n. Okay, so it'll probably be a set cover. Okay. So that's 2 algorithms for this problem. You can either repeatedly do it or just scale up. Yeah. Oh, okay. Um, good, good. So, well, first, okay. Okay, so now, do you ever have an instance where you actually get a set cover and pay at most log m times opt? Maybe some constant times log m times opt. That's a good question, right? All I showed is that with high probability, maybe this slide would be better. With high probability for any particular alpha, you'll get alpha opt in expectation. So like if it's log n or something, or 10 log n, you'll get 10 log n opt in expectation. And with very high probability, like 1 over m to the 9, it'll be a set cover. And now the question is, will I get objective value roughly 10 log m and also be a set cover ever? And how can we argue this? Yeah. So right now, this thing is almost definitely a set cover and has good objective and expectation. Will there ever be an instance where you get basically good objective? Maybe it goes up a little more and it's still a set cover? Or is it possible there's some weird correlation or something? Mhm. So I guess at the end of the day, you want to hold in your hand a set cover was roughly, where the size is roughly log m times op, maybe times a constant. We showed that, oh, we can randomly create an object that's almost definitely a set cover, and an expectation has log m or 10 log m times opt sets. How can I argue that I can actually get, maybe I can repeat the algorithm or something, but ultimately, how can I argue that ultimately I can really get in my hand something that satisfies both of these things simultaneously? Both good objective, sorry? Sure. So, which one do you want to apply Markovs to? You want to apply Markovs to? So just to go back. So I want to satisfy both objective, roughly log m times op times a constant, and I want it to definitely be a set cover, a feasible set cover. Okay. Now, okay, Markov's inequality. How? Okay, on the objective. Okay. Yeah. Okay. So with probability 1/2, you're going to get at most 20 log m opt, and it was probably 1 over m to gazillion. It's going to be a set cover. So by the union bound, you'll get both. It's probably close to 1/2. Yeah. All right. Good. Good. And then if you wanted to like not give up a factor of 2, if you want to just like only give up a 1 plus epsilon or something, well, you know that epsilon fraction of the time it's only going to go up by 1 plus epsilon, again by Markov's inequality. So you can repeat 1 over epsilon times the algorithm. And then you don't have to pay so much in that objective. Okay, good. So let me give a slightly more general form of something. Yeah. I mean, so there we give up a factor of 2. But if you want to give up a factor of 1.1, yeah, yeah. And you can make it arbitrarily small and you just have to repeat more to get success. Okay. I should also mention that because you have an LP solution, after you sample and see what you got, you can compare the number of sets to your objective value from the LP. Because we really show that it's 10 log m or log m times the LP opt. So you can double check if you got something that you're happy with, which is also helpful, right? So then you can repeat until you get what you're looking for. Okay. So let's do something that's just generalizing this. So this will be quick, and then we can actually start the next topic. So this is a covering integer program. Okay, it's like set cover, but with coefficients and costs. Okay, so we're just exploring a generalization. So, so first, I have these costs in the objective. So taking a set, so to speak, you pay different amounts for different sets. And now we have coefficients. So you're trying to get this, for a particular point I, you're trying to get this sum to be at least bi. Okay, so you want to take, so to speak, as few sets as possible, so that the sum is at least bi. Okay, so you just imagine this comes up often in operations research or something. You're just trying to take the minimum amount of stuff to satisfy a bunch of constraints where do you have enough of this? Do you have enough of that? So on and so forth. But very similar. And so you just relax the LP like before. Okay. And now, same question. Very similar setup. I want to take some fractional solution and turn it into an integer solution. Any ideas? There's like 10 people doing their like imaginary talking. Let's try the same thing. Okay. Now, so we're going to try the same thing. We'll scale it up by a factor of alpha, pay that in opt, but now we want to argue that we satisfy all the constraints. So I'm just focusing really on that analysis. Okay. So maybe as a quick disclaimer, this is actually going to be relevant. So I want to point out that I can assume that all of the aij's are smaller than any bi. But why? Yeah, so if this was bigger, like much bigger, xj is equal to 1 is easily going to satisfy bi, right? So if I decrease aij down to bi, all that matters is whether or not xj satisfies it by itself. So for an integer program, like there's no point in getting more than bi points from a decision, right? Because you're just trying to satisfy this inequality. So all the aij's that are bigger than bi, you can just drop it down to bi, and it'll be the same. So that's helpful. We'll see for technical reasons. Um, looks like I just have the same slide again and again. Okay, I see. Okay, so I want to analyze this algorithm Z, which is just scaling up xj by alpha. Now, one thing I'll point out is that last time with set cover, it was a 0 or 1 solution. As presented in that covering integer program thing, it's actually a, sorry, it's any integer. Okay, I'm just trying to round it to an integer. So that's why in the notation you have it either goes up or it goes down. Okay. All right, so this is like the probability of, maybe I should make this strict. This is the probability of failing a particular constraint I. Okay, so I scale up Z and then I randomly round up or down to the nearest integer. Very similar to what we did for set cover. And I want to do the same analysis. What are the odds that I don't cover this constraint I? And how do I analyze it? What should I write? Okay, so, oh no, I've already done that for you. We want to get the probability that's bigger, and it's more convenient to look at the probability that it's bad. Yes, I've already done the negation for you. So this is the more convenient form to directly look at. The probability of messing up constraint I. Yeah, one particular I. Okay. I is a row. Well, I don't know which, the constraints are rows. So maybe you meant column? Okay, that's fine. But this is something very similar to set cover, right? What did we do for set cover? We did this like product of everything not happening. Okay. But why didn't you guys suggest that here? Oh, that's true. Although what I can do is I can write, okay, so the probability of rounding up is going to be equal to alpha xj minus the floor. Maybe I can write it like this. So, okay, that would be our probability of rounding up and rounding down or something, right? So there is some probability. So in set cover, we're modeling something a little bit simpler because you just have to have all the sets fail to be taken. But this is like, oh, there's many ways to fail. Maybe you take some, but not enough. Sorry, right? So it's a bit more general this time. So how do we deal with the generality? That's at the end. So I'm going to try to show that this one particular constraint is really good with high probability, so I can take a union bound. So that approach is going to be similar to set cover. Here, I'll go to the next slide, which is basically the same thing. Okay, how about now? Okay, so we can try to use the Chernoff bound. Okay, so these are all, each of those aij's are at most bi, so they're kind of bounded, right? In fact, you can imagine dividing everything by bi, in which case these are all at most 1, and this is equal to 1. Okay, so we can scale down. Okay, so okay, so the odds of being okay, so in the Chernoff bound, we want to identify mu, basically, right? So okay, so first let's do this. So what's mu, which is equal to expected value, and I'll do it in the normalized form. Aij over bi. So these are all values between 0 and 1. Okay. All right, so what is, oh, zj? What is this? Yeah. Okay, so let me sum over all j, aij over bi, and what's the expected value of zj? Alpha times xj. So the rounding up and rounding down is set up so that in expectation it's okay. Okay, so and then this is at least not 1, but close alpha. Okay, so this quantity, I'll write in different color, this is equal to this probability that the sum of j, aij over bi, zj is at most, so it's at most 1, but 1 here is something like, compared to mu, this is like, if it was 1 minus epsilon, then epsilon would be equal to like mu minus 1 over mu or something, right? Is that right? Yeah. So epsilon is like at least a constant, okay? It's very big compared to what we did before. Okay. Now, okay, one thing that's a little bit annoying is that usually we do the x's between 0 and 1, and these coefficients, I mean, z might be kind of big, right? Z could be going between 5 and 6. Okay, so how do I deal with this? So the key point, so aij over bi is at most 1, so that's good. Now the key point is that the random part is still plus or minus 1, right? If it was going between 5 and 6, you have like 5 plus or minus 1. So the randomness is just 1. So there's many different ways to think of it. But one way is you can think of, if it was between 5 and 6, you can imagine that as 6 random variables between 0 and 1, where the first 5 are always equal to 1, or always, rounding up. Okay, so what really matters is that each of these independent flips only change the total sum by at most 1. You can also directly and kind of reprove it, and I can give a slightly more general form down here. But the lazy way is to just imagine that those constant parts are just, small individual things that are always constant. You'll still have independence, right? Because no matter what the constant comes out to be, it doesn't affect anything else. So that's not such a big deal. And so you're going to get something like e to the negative epsilon squared mu over 2, where epsilon, at least as long as mu is at least 2 or something, is big enough. So I'll just write e to the negative epsilon squared over, sorry, mu over 4. So we're just going to treat epsilon as a constant. Okay? So now, and mu is alpha, or mu is at least alpha. So we have something like e to the negative alpha over 4. And now if I want to make this useful, what should I set alpha to? Okay. I think you're all on the right page, but then nobody wants to be loud about it. Negative 2 log n or something, and you get your, so that's an m, 1 over m squared. Okay, and now the rest follows. So this is the exact same as we did before. It's just that with general sums, you now use Chernoff bound to come to the same conclusion. But it's also interesting, right? Because a Chernoff bound up to some constant factor of 2 or something, who cares, got the same conclusion as, the odds of deviating significantly from the average is basically the same as all tails in the previous experiment, right? There's not a big qualitative difference. So the Chernoff bound is very strong. Okay, so that's how you deal with that. Okay, great. So, uh, you guys want to do something fun or something boring? Okay, so I'll keep deferring the proof of the Chernoff bound, and I'll get us started on online algorithms. Okay, so this will get us going so that hopefully we can